Hello viewers, welcome to Jonas Research, and today we are going to learn about chi-square. We already know chi-square, we have been taught in class and how to do it manually as well. And have you asked yourself, if you have a complex data set, how are you going to do your chi-square analysis? So R is really going to help us to do our chi-square analysis, whether we have a small data set or a complex data set. We already know that with the you solving it manually, you are going to spend about months trying to solve a big data set as well. So let us remind ourselves on the definition and some types of chi-square that we have. So chi-square, we already know that chi-square, they are tests, basically statistical tests that are used to determine whether there is a significant association between two categorical variables. So this one we're talking about categorical what? Variable, or whether an observed distribution differs from what? An expected one, whether you have what you are observing and what you expected to be, whether they are what? Equal or not. So we already know the two types of chi-square that we have. We have the goodness of faith and the chi-square test of what? Independence. The chi-square test of independence is used to check if two categorical variables are what? Related, and that of the goodness of faith is used to check if a sample matches an expected what? Distribution. So today we are going to start with the goodness of faith. So with the goodness of faith, I'm just going to generate any random data that I want. So with the random data, I just decide to name it national demographics. As we have the, I use the rep. You already know how to generate any data that you want in R. You can check on our previous video to learn how you can generate data in R. So I'll use the rep just to replicate the white 100,000, black 50,000, Asian, and others. I just want to generate a data on my own. So I run it and let's see how the data will be. You can see that it will be a very complex data set. You can see even it's only the white that came. Even the white was what? 100,000. You can see the white that came. It's a rich get options. So that means there are so many down there as well. And we did another one just for the sample. So this one is for the population, this one is for the sample. You can see that the white here was for 100,000, I did it 600 over here. The black was 50,000, I did it 250 here. The others was what? 35,000, I did it 150 here. So you can see that this is the sample. I'm just taking it from this what? Population. So this is the expected, and this one is the what? Your observed one. You were expecting y to be 100,000, but it came out to what? 600. So these are the expected and the one you observed as well. So let's run it. Yeah, so let's use table, that frequency table. In the previous video I taught you what we use frequency table for, just to find a general view of it. So frequency table of our expected, you can see how it is. The Asian was what? 15,000, black was what? 50,000. And let's do that for our what? Observed one. You can see that observed, it was what? 75. The black was what? 25. Others 150 as well. So now we relate our what? Observed to the what? Table. But without that, let's start with the manually. We just want to solve it manually, and we're using the chi-square function as well. So I'm just going to teach you how we are going to solve it manually. After we go to where we can use the chi-square function just to go straight forward. So we're solving it manually. You know that chi-square, the function, the formula for it is sum. You know, the sum, we have the summation sign as well. But this one, because we are doing it we are going to use the sum function. So sum, open bracket, we have the observed, that's what you observe, and what you expected it to be, all squared, all divided by what? The expected. So that's basically what chi-square, the formula for chi-square is. So we are going to, the observed one is the one down here. That's the observed data that we have. This one, as you can see, they are smaller than the expected one to be. So I'll equate that one to the observed, So I said table, that's the table of the observed, that's this one. I'm just giving it a variable name called observed so that we can put it in our formula as it is. And to get your expected, they say that with the expected, you're supposed to find the probability of the expected multiply by the number of what? The observation. The number of what? Observation. So in order to find our expected what? Value. So that's how when we're doing it manually, that's why we were being taught. So I'll just find the probability. So use the prob dot table. This one was well explained in the previous video in the frequency table as well. So I use prob dot what table. So this will give me the probability of the what? The expected what? Value. So you can run this and see how it is. So you can see that's already giving me the what? Probability of them. And now your probabilities, which now I'm giving the national what ratio, the probability times the length of the what? Observation. So I'll run it and I'll check how it is. You can see now the values. So our expected Asian is now 79.32692, the black 2 as well. So I'm going to use the formula as I said earlier on, the sum of the observed minus expected all squared divided by what? The expected. So I'm going to run it and now find the statistical test. You can see that it's 18.19481. So the chi-square statistic is what? 18.19481. So we are going to use that. We are going to use that in making conclusion. But before we know that, we are supposed to know our what? Critical value. We are supposed to know our critical value. So in order to know our critical value, we are going to solve for our critical value as well. So with our critical value, because when you are solving it manually, we can't find p-value, you know, in your manual calculation. You get me? You can't use, so we normally use a critical value. But when we are using the chi-square function, it will just give us the p-value. So we just compare it with the p-value of 0.05, that's the alpha value, and we just go straight forward. So with the chi-square, if you want to find a critical value, you use the keyword cris-q just to find the critical value. It's basically define the critical value. So we just tell you that our significance is what? Value is what? 0.95 and want the degree of freedom to be 4. So we are just assuming. So the degree of freedom should be 4 because the number of variable, the number of variable 1, 2, 3, 4. So we will just subtract 1 if you remember how to solve it manually in your analysis. There's it. So degree of freedom is equal to number of variables category minus what? 1. That's the degree of what? Freedom. If you remember how we solve it manually, you know what I'm talking about. So you run it. So this are what? Our critical value. So now we know that our critical value is 9.487729. So our test statistics was 18.19 blah blah. So you can see that our test statistics is greater than our critical value, and our null hypothesis, and in the t-test I gave you that we have null hypothesis that they are just assumption for us to make decision on. So with the null hypothesis for goodness of fit, it is for the null hypothesis, it means that the observed frequency matches the expected frequency. That's for the null what hypothesis. And the alternative states that the observed frequency do not match the expected what frequency. So the null is saying that it matches, and the alternative says that what it doesn't what match. Do you get me? So in the decision making, so far as your test statistics is greater than your critical value, so you reject what the null hypothesis, and you conclude that the observed what frequency do not match the expected what frequency. Do you get me? So basically doing it manually, this is how you're going to explain it. So you say that in conclusion, since that your test statistics is greater than your critical value, we reject what H naught and conclude that the observed frequency do not matches the expected frequency. That means your sample size or your sample doesn't mimic that of the population, or what you observe doesn't mimic that what you expect it to be. So basically that's what it is. So we just go straight and solve it using the chi-square function, straightforward. Basically I was teaching you how to do it manually, so now we are going to use a chi-square function. Do you get me? Yeah. So this one is just you finding the p-value if you want to use p-value for conclusion as well. So let's use the chi-square test and do it, and let's compare the answers, whether we solving it manually and we using a chi-square test, whether we get the same answers or not. Do you get me? Yeah. So this one with a chi-square, we say chi-square test dot test open bracket, your x is the observed and the p is the national ratio. That's that of the expectation as well. So you just run it, and now you can see, yeah, the x squared is equal to 18.195. As we did it manually, we saw the degrees of freedom is 4, as I showed, the number of variable minus 1. Yeah, and the p-value is what, 0.00118. You can see it over here. When we did it manually, you can see it over here. So yes, since the p-value is less than 0.05, we reject H naught and conclude that the observation is not the same as the expected, or doesn't mimic that of what we expect it to be. Do you get me? So basically that's for the goodness of fit. Okay, so we are going to start with the chi-square test of independence. So since we know the goodness of fit, you're supposed to also do that of the chi-square test of independence. So with the chi-square test of independence, that's where we are going to test whether the two categorical variable or data that we have, whether there's an association between them or not. So I'm just going to generate any data of my kind. So I'll just go straight. I'll say set.seed. That one is to randomly give me any data that I want. So I'll just run. Maybe if you run yours, your values will be different from mine. That doesn't mean you are wrong. You're also correct. Your values will be different from mine. So I just use sample just to generate any data, just raise data, total raise. So white, black, and their probability, and you replacing them as well. So I'll just give you a general view of it. So basically this is how it is: the Asian, black, like that we do for the goodness of it. So this for our first sample, so I'm going to do that for our second sample as well. So let's just observe. Let's find the table of our second value, and let's see how that one too will be. So voter underscore party. So ready here. So you can see this one too as well. So we just want to know whether your race does it have any association with the party that you join, the race that you are, whether you are an Asian, whether you are black, or whether you are white. Does it affect the political party you join? Maybe USA, if they want to vote for Donald Trump or maybe Barack Obama, they are supposed to know. Do you get me? Oh, those who are blacks, because of Donald Trump policies, we want to know whether the blacks will vote for Donald Trump or not, or whether they will vote. So your race, whether you're black or you're white or you're Asian, does it really affect the political party that you join or not? So that's basically what we want to know. We want to know whether the association is there. between the race and the political party you join. And the null hypothesis for the independence is saying that there's no association between the two variables. There's no association between the two variables. And the alternative says that there's association between the two variables. So now we are going to use our p-value to determine whether there's an association or there's no association. Remember, if the p-value is small, we reject the null hypothesis. Whether if it is less than 0.05, we will reject the null hypothesis. So put that at the back of your mind. That's what we are going to use for all. So I'll just use my chi-square finite square dot test, and the x for the first variable and the y for the second variable. So you can see that the independence here is very simple and just precise as well. So I ran it, and you see Pearson chi-square tests our data, voter race and voter party. So you can see that the p-value is 0.3296, 0.3296, which is greater than our alpha value of 0.05. It is greater than our alpha value of 0.05. So we will conclude that we will fail to reject h naught because it is now greater than the 0.05. So we will fail to reject h naught, which is the null hypothesis. So it means that there is no association between your voter race and the your voter party as well. So p-value, let me write it so that p-value is greater than alpha value, which is 0.05. So conclude that. So let me say fail to reject, fail to reject now hypothesis and conclude that let me write it here. Conclude that there is no association between voter race and voter party. So you can see that there is no association between the voter race and voter party. Whether you are black, you are white, it doesn't depend on the race you are. It doesn't affect you joining a particular political party or not. So today we have learned about chi-square and the goodness of it, and chi-square test of independence as well. So we have learned something about chi-square. So if you have any question, you can put it in the comment section. We answer you, then we'll move forward. Thank you very much, and God willing, next time. See you all. Bye.